Okay, so our fourth unit was about the mole concept. That was something that we started to incorporate a lot more math into what we were doing. So, first off, remember the mole is a concept that chemists use in order to be able to count things by weighing them, because of course the items that chemists talk about, being atoms and molecules and formula units of things, they are so small that it's really difficult to kind of conceptualize how much of these things exist in certain samples and even small samples of things that we use in labs. So we do have three conversion factors that we use the mole with. The first one is, of course, 6.02 times 10 to the 23rd particles is what it's equal to. But particles is equivalent to atoms or molecules or whatever the formula units are that we're talking about. And this was also called Avogadro's number. Right, so that's what we use to identify or put a number value to the mole. It's no different than when we say 1 dozen equals 12 things. One pair means two, right? So on and so forth. It just so happens that 1 mole is 602 sextillion of those things, whatever we're talking about. In terms of another conversion factor, we did have the molar mass that we began to calculate using the average atomic masses on the periodic table that we can identify as the equivalent of how much 1 mole of something weighs. So we always say that this is in grams from the periodic table. And the last one that we did was liters in terms of being able to identify mostly gases and 1 mole and how they are equivalent to one another. And this is when we said at STP, which is standard temperature and pressure. That's just when we can use this value. So whenever it says at STP, that's just letting us know, hey, it's okay to use 22.4 liters equivalent to whatever the mole values are there, or grams, or whatever the mole map is showing us, because we also did have our mole map for this unit. So calculating the molar mass of calcium phosphate, remember we had to identify first how much each of these elements weighs on their own. And even though there's a polyatomic here, we do treat every element separate in this case, because there are they have different masses respectively. So we want to make sure we incorporated all of the element weights. It's kind of like going shopping, right? You figure out how much of one thing you need to buy. You also think of how much that one thing costs, and you multiply it by however many there are, and you get a total in the end by adding up all of those values. So magnesium has a mass of 24.31 grams. Phosphorus would be 30.97, and oxygen would be 16. And we have 3 magnesium that we have to take into account. We have actually 2 phosphorus atoms that we have to take into account, and we have our 8 oxygen. Where I'm getting those numbers from is one of 2 ways. You can either act like this is distribution and just say, oh, this is actually 1, since there's nothing there. 2 times 1 is 2. 2 times 4 is 8. Or you can just say 2 PO4 groups would be written out like this, and then you can count everything like that as well. So you can do it either way. But that's what it's showing you physically. So we get our values here. I'm going to do some calculations just on my calculator over here, just to make sure that we're all on the same page. And then I'm going to do some a little bit later on in the calculator on the actual iPad. So I get 72.93 there for the contribution of mass for the magnesium. I get 30.97 times 2, which is 61.94. And then I get the 16 times 8, which is 128. And then, of course, like any total that you would get, you would just add those together to get your final molar mass, which in this case would be 61.94 plus our 72.93, and we end up with 262.87. And of course, our unit for this is grams per mole, because, again, this is the molar mass. That is how many grams 1 mole of our magnesium phosphate here. And I'm sorry, this should say magnesium. I apologize there. So good thing I caught that. All right, so our magnesium phosphate, how much that weighs per 1 mole. So going by that exact same idea, how much does 1 mole of the following weigh? Really, we're just finding the molar mass. That's another way to ask that. Carbon is just 12.01 grams per mole. And instead, because it says how much does 1 mole weigh already, I'm just going to say this is how much it weighs. We know that it's per mole anyway. Bromine gas, your first instinct might be to put 79.90 grams. However, we do have to multiply that by 2 because bromine is part of Hänkelbrief, which means it's actually Br2. So 79.9 times 2 gives us 159.8. So there's 159.80 grams equal to 1 mole. And then over here we have our aluminum. We know that aluminum has its own mass, sulfur has its own mass, oxygen has its own mass. Aluminum is a mass of 26.98, and there are 2 of them. Sulfur, 32.07, and there are 3 of them. And oxygen, I said oxygen, I wrote O, 16 times 12. All right, so if you were wondering how to put this, or how I'm putting it in the calculator, you can do it one of 2 ways. I personally like to do it all at one time. You can do them separate, kind of like we did above, and then add up the results in the end. I'll do it a different way here for you. What if I just put everything in, and what I would make sure you do is use parentheses so that order of operations stick together. So put parentheses around everything when you plug it into the calculator, and you should get you should be able to do everything all at once. So what that looks like is this. After every multiplication operation I'm going to do, I'm going to put it in parentheses, 16 times 12. And we should end up with 342.17 if my math is correct. And there we go for our aluminum sulfate down there. So now that we're comfortable with finding the molar mass, really in terms of our equivalents for all of our calculations here in our mole map, you notice that all of these values are equal to 1 mole. So as long as we can get to the unit of the mole, we can go from particles to mass, or we can go from liters to mass, or liters to particles, right? It really doesn't matter. Because we know that the mole is the bridge to all of those. So how many moles are in this many grams of HCl, or hydrochloric acid? You want to, of course, show your work. Moles, of course, I like to underline what we're given, not just number value, but unit as well, and that's what I'm always going to start with for all of my calculation problems. And I want moles in the end. And what I can do is I can go directly from grams to moles using my molar mass. And the difference, we see that these conversions, all of them, well, 2 out of 3 are always the same. The only one that's going to change is the molar mass, depending upon what substance we're working with. So if we were working for bromine gas, my molar mass would be 159.80 grams. But in this case, I'm working with hydrochloric acid, which would mean that I have to figure out what the molar mass of hydrochloric acid is. And if I do that, I know that it's going to be hydrogen and chlorine, 1.01, 35.45, and add those together, and I should end up with 36.46 grams per mole. Grams per mole tells me that there's that many grams in 1 mole, so I can then proceed with my calculation, and we put the first number and unit over just the number 1 to show that it is effectively a fraction. That's basically you know, all whole numbers are really over 1 if you think about it. And we get the visual to be able to cancel out our units using our unit conversion method, which we refer to as dimensional analysis. So, or factor labeling, you might have heard it called too. So we like to just do these unit conversions. I like to put the units in the spaces that they need to be first before I put any numbers. We know that now that I see gram is the unit on the bottom, that's going to be where my molar mass goes. That's equal to 1 mole. Every additional fraction that we include is a conversion factor based on how many bridges we have to cross in our mole bridge. So doing this, we get 28.5. And you can simplify these if you want. Really what we're doing is we're multiplying everything that's on top, and all the numbers that we find on the bottom we divide by. And we end up with this, which would be 0.781. So if you wanted to simplify, that's 28.5 times 1. Down here, that's 36.46 times 1. And then we just divide by each other, which gives us 0.78 moles. That is our final answer there. All right. How many particles are in a water are in a 5 gram sample? So I underline what I start with. I circle what I want. 5 grams is what I'm starting with over 1. Now, I cannot get directly from grams to particles. Remember, we count by weighing, and that's because we use the mole. So I first need to use my bridge to go from grams to moles, and then, and only then, will I be able to go from moles to particle number. So we actually needed to cross 2 bridges on our mole map, which in this case allows us to add on the 2 conversion factors that we need there. So now I can start to look at what I need. I know that I need to find the molar mass of H2O. H is 1.01 times 2. O is 16. You add those all up. When you get your answer, it is 18.02 grams per mole. So I know that 18.02 grams are equal to 1 mole. I also know that 1 mole is equal to 6.02 times 10 to the 23rd particles. Everything will cancel out, and you are left with the unit that you want, which is particles. And so let's simplify the top. So we get 5 times 1, which you can ignore, times, and remember, 6.02. And then we have our E function here, second comma, and then you can just put 23. You don't need to worry about any multiplication symbol. You don't have to worry about 10 or carets, right? You could just put it in as the calculator as so, and then we get an answer, and that is going to be the simplified part of the top. Now you see that E there. Don't forget that. That is part of your answer. Over, well, the only number that's not 1 at the bottom there is 18.02. And so we're going to take our 3.01 times 10 to the 24th in parentheses and divide it by 18.02. And that gives us 1.67 times 10 to the 23rd particles. So that is our final answer here. All right. Next up, determine the percent composition of all elements in magnesium phosphate. Lucky for us, it's almost like this was planned. Lucky for us, up here, this was the work to figure out the total mass of magnesium phosphate, right? And so we actually have all of our values here, and we ended up knowing that the total mass for magnesium phosphate up there was our 26.87 grams per mole. And so when we're talking about percent composition, any percent is based off of part out of whole, right? And so in this case, when we say part, it's the individual mass of the elements over the total mass of the compound times 100 to create a percentage there. So here is our total, And so with that total, what I do is I take all of those individual masses for each element separately that they contribute, and I put them over the total there. So all of these will have the same denominator, right? Because they all are contributing to the same compound. So every total here should be 262.87. Whoops. Times 100. And so I just have to fill in the blank at the top. And what I do is I look at the total amount that those individual elements make up for the mass, not just the individual amount of each element. I have 3 magnesium, so I know that there are 3 contributing. So my individual mass here for the magnesium is 72.93. So on and so forth. So I get 61.94 for the phosphorus, and then I get 128 for the oxygen. And then I can go through and I say, all right, what's 72.93 divided by 262.87? Did that work out? Nope. There we go. All right, times 100, and we get about 27.7%. So that is how much just magnesium contributes. 61.94 divided by our 262.87 times 100, 23.6% there. And then you could find this last one of 2 ways. You could do it exactly the same way, which I will do, or you could know that the total percentage should equal 100%, right, by adding up all these percent values. So if you know 2 out of 3, or you're just missing 1%, what you could do is just add the 2 that you have and then subtract it from 100, and you should get the same answer. And you can confirm that by yourself if you want, but times 100, we get about 47.7% here. All right, so ideally, if math works, it should be pretty darn close to 100, and holy cow, it is. So very nice. So that's how you do our percent composition. In this case here, we see a chemical reaction produces this much hydrogen gas, so 2.50 grams. Hydrogen gas is H2 because it is part of Hänkelbrief, which means its molar mass is 2.02 grams per mole. Anytime I see the unit grams or the word mass anywhere, I know I have to go to the periodic table and find those molar mass values, or those masses. Here's what I was talking about is assume at STP, because we are looking for the liters that this sample of gas occupies based on how much it's weighing. So I have 2.50 grams over 1. I cannot go from grams to liters, just like I couldn't go from grams to particles. So I must make a pit stop at the mole as a unit first, which then will allow me to go from mole to liters, right? And we use our conversions. Grams are on the bottom, so my 2.02 go on the bottom here. That's equal to 1 mole. And then I know that 1 mole is equal to 22.4 liters of anything at STP, or standard temperature and pressure. Grams go away, moles go away. Liters is what I'm ending with. Let's simplify at the top, which is 56. Divided by my 2.02, and I get 27.7 liters. And that's my final answer. And last but not least, we also did our empirical formula work here in this unit. That was when we were solving some crimes and stuff. So this was pretty fun, pretty applicable concept as well. So we went through a little little systematic way to go through these. What we can do is start with all of the elements that are within our compound, and we start with a percent of each. So here I have 62.6% carbon, I have 10.3% hydrogen, I have 27.1% oxygen. So we can go from percent to grams, so percent to mass, because we're assuming out of a 100-gram sample, and if these percentages are out of a 100-gram sample, then those are the actual values of the mass of what the contributions are by each of these percent compositions that we're given. So this is actually just 62.6 grams. So percent to mass. And then we say, well, we can't do anything, and all of our subscripts in all of our compounds, kind of like the 3s and the 4s and the 2s that we see in our formulas, those are all mole ratios, not gram ratios. So we go percent to mass, mass to mole. So percent to mass, mass to mole. So I'm going to be using the, I'm going to be using the molar mass of each of these elements. Now, these are going to be each of these elements individually. So just because it's hydrogen, I'm not going to say H2, just because we don't know how many. We're dealing with the element by itself, all alone. And so in this case, it would be 12.01 grams is equal to 1 mole for carbon. 1.01 grams is equal to 1 mole for hydrogen. 16 grams is equal to 1 mole for oxygen. And so we get mole values, and so we had percent to mass, mass to mole. All right, so I'm going to get all of my mole values to get mole ratios here. Oh, yeah, 62.6 is itself. Until you divide it by 12.01, and then we get 5.212. I think that it's really wise to, when you get your mole values, to go to at least the thousands place or 3 decimal places, just because if you round too soon, your ratios could be off a little bit. And if you round incorrectly, it could be that way as well. So I'm getting my mole values at 10.198 here. I get 27.1 divided by 16. And we get 1.694. And so we just did percent to mass, mass to mole, divide by smallest, then we're going to round or multiply till whole. All right, that's a nice little rhyming way to identify this. So we first identify that this is our smallest mole value, so we are actually going to divide all of the mole values that we just calculated by that even itself. And ideally we end up with, let's try that again, 694. Not the other way around. Ideally, what we get are these ratios where we can just round to the nearest whole number, and then that'll be our subscript for that, for our empirical formula. Now, we do have fixes, right? If it's 0.5, if it's closer to 0.5, we multiply everything by 2. If it's closer to 0.33 or 0.66, we multiply everything by 3, so on and so forth. And you would be given that those fixes there as well. You're not necessarily going to have to memorize those, but in this case, let's see how this works out. So we know that one of these ratios is always going to be 1 because we're always dividing the smallest by itself. Then we do the same thing for the other. So this is 5.212 divided by 1.694. That gives us 3.08. And because this is 0.0, this is really close to being able to just be rounded down to 3. So we do that. And then we have 10.198 divided by 1.694. Similar deal here. This is 6.02. That is really, really close to 6. And so we were able to round to the nearest whole number here, which is phenomenal. And that makes us a lot happier. So there are 3 C's here. There are 6 H's and 1 O in this empirical formula here. All right, so hopefully this is a nice little refresher, and hopefully this helps in all the calculations for the mole. All right, one more unit to go.